Well, good afternoon, everyone. I'm going to re-record the cation exchange lecture, which the audio didn't work on before the break. So we'll just head straight on and do that. So cation exchange reactions and soils are pretty important. We reflect that by running a practical class on that, which many of you have done or are about to finish. And we have some learning outcomes for you for the lecture. These are on LMS, so I'm not going to spend a lot of time going through those blow by blow. We're just going to get to the meat of the lecture straight away. So cation exchange capacity is kind of one of the central concepts, and it's the amount of negative charge per unit mass of soil, and has, I guess, what look initially like odd-looking units. But we'll get to that in a minute. So really what we measure is the maximum amount of cations that are able to be retained by the soil by cation exchange. Cations can, of course, be retained by adsorption. We don't consider adsorption mechanisms in that measurement of cation exchange capacity. It's just electrostatic cation exchange reactions that we're interested in looking at. So we can't directly measure the amount of negative charge on the soil. It's rather a difficult thing to do. So what we do is we measure the amount of cations held. And what you do in the lab, as you know, is we saturate the soil with a strongly attracted cation like silver, thiourea, Ag2U+, and we use the change in concentration of a fairly concentrated silver solution to estimate CEC, and you'll find out more about that in the lab, and particularly by reading the lab manual. So we measure cation exchange capacity in moles of charge per unit mass, and the unit that we're using in this unit, pardon the overlap of terms there, is centimoles of charge per kilogram. And that is really for historical reasons because it's numerically equivalent to the old unit that we used to measure cation exchange in, which is milliequivalent, so millimoles of charge per 100 grams. Those two are numerically the same if you figure it out. Okay, so cation exchange capacity in diagrammatic form just looks a bit like this. So the total amount of cations that the soil can retain. Notice that cations can be held electrostatically around organic matter because we know that organic matter can have a negative charge. Cations can be in exchangeable form on the planar surfaces of clay minerals, shown by these stacked layers here. And you should remember why we express clays as stacked layers. And in some clays, it's the interlayer cations that are also exchangeable, but that's not the case for some clays like illite groups. The cations are retained too tightly in the interlayer, right? The higher the cation exchange capacity, the larger ability a soil has to store plant nutrients in potentially bioavailable form. And because different compounds have negative charge, or different materials in soils, specifically clays and organic matter generally contribute to our negative charge in soils. Cation exchange should be higher for a soil with higher clay or with higher organic matter. And remember that the sum of the negative charge is dependent on pH. So the functional groups on organic matter dissociate to give negatively charged versions of themselves on the organic matter molecule, and that dissociation is more at higher pH than it is at lower pH. So what we should see is that a soil with lots of clay, lots of organic matter and high pH should have a very high cation exchange capacity. Okay. Just some more concepts that we need to cover before we get into this proper. So moles and equivalents. So for monovalent ions, 1 mole of atom is 1 equivalent or 1 mole of charge. But for ions of higher charges, it's a little bit different, but it's quite simple really. So if we have a divalent ion like copper, 1 mole of copper is 2 equivalents or 2 moles of charge. And similarly for a trivalent 3+ cation like aluminium, 1 mole is 3 equivalents or 3 moles of charge. Right? And a centimole, which is the unit that we're using, centimoles per kilogram, is just 1/100th of a mole of charge. And that gives us nice numbers, basically. Numbers usually for Western Australian soils somewhere between 0 and 6. More details on that in your lab manual as well. Some more concepts. Base saturation. Okay. Before we do that, one of the the learning outcomes was that you would know the ions for which cation exchange is important, and they're all on the screen right now. The ones that we usually consider, particularly from a bioavailability point of view, are sodium, potassium, ammonium, calcium, and magnesium. And these are what we call the base cations, or just bases. There are historical reasons for that as well, and it does make sense. If a soil has higher pH, that is, it's more basic, these cations will be much more abundant than the other acidic cations, hydrogen and aluminium ions, and they, together with the base cations, will dominate the cation exchange capacity. So exchangeable cation reactions in soils are important for these elements: hydrogen, aluminium, sodium, potassium, nitrogen as ammonium, calcium and magnesium. Total exchangeable bases, we can define a parameter which is just the sum of our exchangeable bases. Often we don't consider ammonium in that because it's a transient cation in soils. It's rapidly assimilated by plants and microorganisms, and it's a little bit more difficult to measure too. And we use a slightly different definition in your laboratory manual. We'll just consider sodium, potassium, calcium, and magnesium. Okay, it's useful to know that because it allows us to calculate base saturation. So base saturation expressed as a percentage as total exchangeable bases, the sum of these expressed as a charge, not moles of charge, not moles of element. So we need to multiply the concentrations of calcium, magnesium by 2, of course, divided by the cation exchange capacity times 100. So it gives the proportion of the cation exchange capacity occupied by base cations, these ones here. And generally, the higher the base saturation, we consider that to be an indicator of good chemical fertility. If we have a lot of hydrogen ions and aluminium ions on our cation exchange materials in soils, then that's often a soil which is depleted in these essential ions for plant growth and represents low fertility. Okay, here's a question for you. I would hit the pause button at this point because I'm just about to show you what the answer is. So we want to completely exchange 10 centimole charge per kilogram of calcium. How much do we need? Is one of these right? Well, in actual fact, this one here is right because moles of charge balance moles of charge, right? Okay. If you didn't get that, you might need to go back a slide or two or look at a textbook and revise some of those things. Okay, you don't have the opportunity to ask questions online. We're going to have a look at some of the factors affecting cation exchange reactions, one of which is competition between ions. And the main thing determining competitions is the charge on the cation, or more specifically, the charge to radius ratio. Okay, so let's have a look at this. We've got an unusual looking graph here, so I'll explain it. What we've got is the amount of calcium in solution and the amount of calcium on the clay. So this is vertical axis measuring exchangeable calcium, and the horizontal axis measuring the calcium in solution, but not as a concentration, as a fraction or proportion of ions in solution. So when the fraction of calcium in solution is 1, there's no other cation in solution. And when it's 0.5, in this case, we've got half calcium, half copper. And the same arguments go for the vertical axis, right? So we can see that when we exchange a divalent calcium with a divalent copper, there's an approximate one-to-one relationship, okay? The proportion on the cation exchange surface is approximately equal to the proportion of that ion in solution. So that would be, at, for example, 0.4. Proportion of calcium in solution is 0.4 on exchange surfaces, meaning that there's 0.6 of copper to make the total proportion of either exchange surfaces or solution up to 1. Okay, now what happens when we change cations? Well, let's deal with some of the ideas first. Cations are more strongly held if they have high valency. So aluminium should be able to displace calcium quite easily from the cation exchange surfaces and soils, and also low hydration. So ions which don't have a hydration sphere of water molecules, or ions do, but some have less than others. In fact, it's the smaller ions which are more hydrated because the charge is more concentrated in a small ion than it is in a very large ion, a large nucleus like barium. Okay, well, let's have a look at the effective charge in our graph. So what we've got here is when calcium and potassium, in this case, a monovalent cation, are competing. And we can see that although at this point here, the fraction of calcium is only 0.2, it's occupying just over 0.6 of the surface, meaning that calcium has much greater affinity for the surface than potassium. All right. Calcium, aluminium. Okay, so calcium needs to get to about 0.75, 3/4 of the ions in solution before there's any on the surface at all. And only when its fraction is 1, there's no aluminium at all present, will it occupy all of the surface. In theory, the line doesn't quite go that far. All right, so that explains this valency thing. I don't have an example for you for hydration, but you can imagine the same sort of thing going on a plot like this. For example, barium should be more strongly attracted to the surface than magnesium. So barium-magnesium exchange, if we're looking at barium on both axes, should look a little bit like the red line there. Okay. Now, the other thing affecting the reactions, of course, or the position of equilibrium, is the concentration of ions, and we'd expect that. Okay, the higher the concentration of ion in solution, the more should be on exchange surfaces in soils, and that is summarized quite neatly by the Gapon equation. Okay, it looks a little different from a standard equilibrium expression. So we have what we call an exchange constant, in this case for exchange of potassium by calcium, and the amount on the surface, the ratio on the surface, is equal to that exchange constant times a modified ratio in solution. We take the square root of calcium ion concentration because it's a divalent cation. If it was a trivalent cation, we'd take the cube root as by analogy, and we'd just have a simple ratio if the charges on the ions are the same. Okay. Mentioned soil pH. Soil pH is really important for modifying cation exchange in soils, and that's because of two reasons. One is that, as we know, there are some surfaces where the charge is dependent on pH. There's an example here for something like a metal oxide surface, which is positively charged at low pH, so cation exchange wouldn't occur at all at some pH, say for iron oxides around about 8 to 9. The surface would be neutral, and above that pH, above pH 9 for iron oxides, we have a negatively charged surface. And so, of course, the amount of negative charge available to attract cations is dependent in that case on pH. Right? So that's one reason. The other reason is that the species of ions can change depending on pH. So metal ions like copper and many of the transition metal ions, what we might call the heavy metals, although that's not a very good term, hydrolyze in solution. They react with water to give a hydroxy species. Now, of course, it's still a cation, but it has lower charge. So in this case, the divalent cation copper 2+ would probably be more strongly attracted to the surface than the monovalent iron copper hydroxide plus. All right. Now, similar concepts would apply for anions, but we'll leave you to that. But we know that anions like phosphate change species and therefore change charge in response to changes in pH as well. The type of charged surface is important as well. Different clays, for example, or different types of soil material, comparing clays with organic matter or oxides and so on, have different amounts of charge on their surface, and we've had a look at that already in other lectures. So for clays, the layer in which the isomorphous substitution occurs, if it's in the tetrahedral layer, that is close to the surface of a 2-to-1 clay crystal, the attraction can be much stronger. In fact, in some cases, like the illite clay, is strong enough to make the layers not expanding. Okay, and that's related also to the geometric fit to the surface in illite clays. Okay, and that's We don't have illites as an example, but these are the clays for which cation exchange is really important. Kaolinite, usually relatively unreactive and doesn't contribute much to cation exchange capacity in soils. This is important in Western Australian soils, where most of our cation exchange capacity in many of our soils is contributed by organic matter, because kaolinite doesn't have a lot of negative charge. In soils which have 2-to-1 clays, though, vermiculite and smectites can obviously contribute quite a large proportion of the cation exchange capacity. And remember that the charge on these clays is permanent, not pH dependent. So the substitution occurred during mineral formation, so it doesn't go away. Right? It doesn't change in response to pH. Okay, there's another summary of these things. So organic matter, as I said, very important for Western Australian soils because of its high cation exchange capacity just for the organic matter component, between 100 and 300 centimoles of charge per kilogram. So if you just have a few percent of organic matter in soils, it can change the CEC quite a lot, and different values for different types of clays or other types of minerals. Okay. No, here's our illites, the hydrous micas, which don't have expanding interlayers, and their cation exchange capacity is much lower than the other types of 2-to-1 clay. And kaolinite, that's probably a more realistic value than 1, but still quite low, right? Especially compared with organic matter. And Western Australian soils, often the clay is dominated by kaolinite type clays, just mainly because of the intense chemical weathering that's gone on. So vermiculites and smectites in some cases may alter to give kaolinites given enough time. Okay, if we were going to have a look at teasing out some of these ideas, there's a good data set in this paper here. There's soils from Thailand, soils from anywhere in the world can illustrate things in science. So let's have a look at what parameters have similar depth distributions, and that's what these graphs show. They've got the concentrations on the horizontal axis across the top, and then depth going down, increasing depth go down as you'd expect for a soil pit, right? So let's just blow up a couple of these. Oh, that's not working so well. So we've got, let's change that. Actually, don't know how to change it. Let's try. Oh, we can. Look at that. The wonders of PowerPoint. Okay, so we there you go. Okay, so cation exchange capacity in general higher in the surface soils, but relatively even all the way down. What does it match best? Does it match organic matter or clay? Well, in the subsoil, the cation exchange capacity is probably related to clay content. And we kind of deduce that because the black curves here representing one particular soil are higher than they are for the red soil. And so that's the feature that we see in the cation exchange plot. But in the surface soil, we've got these increases in cation exchange as we get shallower in the profile, so in the A horizon, whereas clay actually goes down. And so the increases in cation exchange capacity in the surface soil are much better explained by organic matter than they are by clay. Okay. Just note that these are oxysols as well. That means they're highly weathered, and so the dominant clay mineral again is probably kaolinite, just as much, just the same as it is in Western Australia. Okay, it's an interesting question for you to ponder. We've dealt with this a couple of times during the lecture, so we will move on. Let's think about putting this into a more applied sense. Soil and environmental factors which affect cation exchange reactions. Well, inputs and outputs of water will change the concentrations of things, right? But all the ions are affected similarly, so the ratios don't change. So even though we can change the concentrations of ions quite a lot just by wetting up the soil or by evaporation concentrating things, we shouldn't change the balance of ions on cation exchange surfaces, because it's the ratio of ions in solution that's important. So even though we diluted or concentrated, the ratio stays the same if we're just adding water. In contrast, if we add things other than water, then we do get some changes, right? So inputs and outputs of ions by leaching. Some ions leach more easily than others. Plant uptake. Plants require more potassium, say, than they require magnesium or calcium. Pollution won't always add every element in the periodic table in even amounts. Fertilizers, we deliberately target addition of some elements, calcium or potassium, for example. Other types of reactions, they result in removal of one ion relative to other ions. Okay, so the concentrations of only a few ions change. Therefore, our ratio in solution will change the balance of ions on cation exchange surfaces according to the Gapon equation. All right. And this is an idea which we will extend when we talk about soil acidification, but here we go. So this is the importance of cation exchange. Plants take up ions from the solution. So the ions in solution in contact with the plant roots can be directly taken up by the plant, and but then the equilibrium would readjust a bit to replenish that ion. So we have a reserve of things like potassium held by cation exchange in soils. Of course, if an ion is released from negatively charged surfaces in soils, it must be replaced by something else. But the plant also has that requirement of electroneutrality. So when it takes up a cation, it'll often release something like a hydrogen ion to balance its own internal charge, and that may be, not always, the ion that replaces something that's removed from the cation exchange surface. Okay, one final thing. In Western Australia, and these data are from Western Australia, there is a much stronger correlation of organic carbon to CEC than just about anything else, except for a few soils where there are many 2-to-1 clay minerals like vermiculites or smectites. So it seems like the main driver of cation exchange capacity is organic carbon content. And so what you should see in your soils is that the cation exchange capacity is higher in the A or AP horizon than it is, say, in the A2 or the B horizon in your soils. And of course, organic matter is one of the things that can change most by management. So lots of cultivation, for example, can deplete organic matter. That means it depletes cation exchange capacity and soil fertility. Okay, so back to our learning objectives. I think we've covered all those, and there we have it.